We're going to be looking at linear approximation and differentials. Okay, so to illustrate what we're going to be doing in this section, let's start off with a quick sketch of a graph, and we'll talk about why this section is called linear approximation. So we'll start off with our xy plane, and let's have a curve f. And at a point A, let's draw a tangent line. Maybe it's right around there. Okay, so again, the situation that we have a point A, and on the graph, on the curve, I should say, it will be A, f of A. And let's call that tangent line at the point A, we'll call it L of x. Okay, and we've been quite familiar with this quick sketch because we know slope of tangent lines is the derivative, and we've been working with the derivative for quite some time. So what we're going to do is a little bit different. So sometimes we've seen functions that are quite complicated, right? We've seen functions that involve logarithms, exponents, our tangent functions, and then composite functions, and then, division and multiplication of functions. So very crazy functions. So we definitely know how crazy curves can get. And the crazier a curve is, the more difficult it would be to find values on that curve. But how difficult is it to find values on a line, y equals mx plus b? It's quite easy, right? You plug in a number, you multiply it by m, and you add a constant. So calculating values on a line, a tangent line, is easy. Sometimes calculating values on a curve is difficult. So what we're going to do is we're going to use the tangent line to approximate values on the curve. And this is why we're able to do that. If we look at this point, this part of the graph right here, where we're taking the tangent line at the point A, we'll see that the blue line and the curve f are almost the same. They're almost the same line. So this blue line, when we're around this point A, f of A, would be a good approximation for the curve. So that's what we're doing. That's what a linear approximation is. So again, what's happening, if we choose values of x around A, we can actually use our tangent line to approximate the curve value, to approximate f. All right, so let's write some of that stuff out. So first of all, our function f is very close to our tangent line L. When x is very close to A. Okay, and because that's true, what we're going to do is we can use that tangent line L to approximate f. Excuse me, to approximate f in that small interval around A. Okay, so let's talk about L of x. we know that the tangent line, let me just kind of jog your memory up here. The tangent line, how we find it is we use this point slope form, right? Whoopsies. Y minus y1 equals the slope, but the slope is the derivative. Okay, so using this formula, let's see, x1 is going to be a, and then y1 is going to be f of a. Okay, so just writing the slope of the tangent line at a using derivatives, L of x is going to be equal to f of a plus the slope. Slope of tangents is the derivative times x minus a. All right, so that's the equation of L. And what we're saying is that f of x can be approximated by L. Remember, approximate is this swervy equal sign. So putting these two pieces together, we're saying that f of x can be approximated by f of a plus f prime of a times x minus a. And then that's the linear approximation. Okay, so this is what we're talking about when we're saying linear approximation. And what we say is that it's the linear approximation of f at a. All right, and so really that means when x is near a. Okay. This is also kind of the same terminology, but it's always a little bit different. When we're talking about L of x, I'll bring back that formula that I had up here in blue. This is called the linearization of f at a. So all of these different, please go away. All of these different terminologies that are saying the same thing. So this is called the linearization of f at a. Okay. Can I get rid of this? Okay. So let's look at an example. How are we going to use this? So we're going to be looking at section 3.10 homework, and we're going to be looking at number 6. Okay, and number 6, we want to find the linear approximation of the function. And I'll write it down here for you guys. Linear approximation of g of x is equal to the cubed root of 1 plus x at a equals 0. And then we're going to use that to approximate some values, okay? We're going to use this to approximate the cubed root of 0.95 and the cubed root of 1.1. Okay, so taking a step back, if we had to figure out the cubed root of 0.95, it'd be really difficult to do that without a calculator. Okay, so our linear approximation might be able to help with that. So linear approximation, there's your keyword. So we know that we're going to take our g of x and we're going to approximate it to a line L of x at around x equals, or a equals 0, x equals 0. I'll put that right here, around a equals 0. And so we know then that this is going to be equal to and I'm going to use this formula right here. So a is 0 and our function's g. So it's going to be g of 0 plus g prime of 0 times x minus 0. So I'm just plugging it into our formula. And this is also nice to write out the formula because then we know what to find, right? So for instance, we're going to have to find what g of 0 is, and we're going to have to find the derivative of g at 0, okay? So always a good step to write out the formula. So let's do a little bit of side work. Let's figure out what g of 0 is. So here's our g function. So we're going to be looking at the cubed root of 1 plus 0. So the cubed root of 1 is 1. And then let's figure out g prime of x. All right. It might be easy. Here, let me do this intermediate step. It might be to find the derivative. Instead of taking the cubed root, what can we do with that cubed root? We can think of it as an exponent. So we're taking it to the 1/3. All right. So now g prime of x, we're going to bring down that exponent, 1 plus x, using the chain rule here, right? So derivative of the outside function, 1/3 minus 1. And then what's the derivative of the inside function? It's just 1. Okay, so then we have to see, I'll clean this up a bit. Negative exponents means we're going downstairs. So then g prime of 0 is going to be 1 over 3 times 1 plus 0 to the 2/3. So 1 to the 2/3 is just 1. So we're looking at 1/3. All right, so we did all of this to plug in up here. So now g of x, it's kind of picking up where we left off, is approximately, let's see, g of 0 is 1. G prime of 0 is 1/3. And then we have x minus 0, which is just x. Okay, so g of x is going to be approximated by 1/3 x plus 1, again, when x is around 0. Okay, so this part right here, this is the linear approximation. So that's the first part. Let's go up to the problem. That's this. That's the linear approximation of g of x at a equals 0. And now we're going to use this line to approximate the cubed root of 0.95 and then the cubed root of 1.1. All right, so let's do 0.95 together, and then you guys can try the next one. Okay, so we're going to approximate this. Okay, so let's think. If we wanted to approximate this cubed root of 0.95, well, we know what g of x is, and we know how to approximate g of x, right? We have this little shebang. So this is our train of thought. We're going to relate the cubed root of 0.95 to g of x, and then we're going to use the linear approximation to approximate it. Okay, so let's remember what g of x is. G of x is the cubed root of 1 plus x. So what does x equal in this case? All right, so in other words, let's see, just a kind of a little equation to solve. You can cube both sides and solve it. And x is going to be negative 0.05. All right, and remember this linear approximation up here for g of x, 1/3 x plus 1, is only good for x around 0. Is negative 0.05 around 0? Yeah, it's pretty close to 0. So I'm just going to make that note. So that's why we can use this linear approximation. So it's pretty close to 0. So that means the approximation will be pretty close. Okay, just going back to our picture, let's just focus on why that's important. It's important to be within this small interval, right? Because then the line looks like the function. If we get too far away from 0, right, then the line is a really bad approximation for the curve. So again, that's why it's important to get those values around A, because that's when your line, your tangent line, looks like the curve. And in this case, we're good to go because negative 0.05 is close to 0. Okay, so then how's that going to work? So we know then that cubed root of 0.95 can be approximated by this line. And what's the x value going to be? The x is going to be negative 0.05. So we can say then that the cubed root of 0.95 is approximated by 1/3. Actually, let's do an extra step just to make sure we're very clear. So this is equal to g of negative 0.05. So it's going to be approximated by our line at negative 0.05. Okay? So what is harder to do by hand? The cubed root of 0.95 or evaluating a linear function at a point? This is much easier, right? So hence the beauty of our linear approximation. So we could do it by hand. I'm just going to tell you what that is because that's kind of some basic arithmetic. But we're going to be looking at 0.9833. Okay, so there you go. So we're saying that the cubed root of 0.95 is approximately this value. All right, so why don't you guys push pause? What you're going to do now is you guys are going to approximate using that same method, the cubed root of 1.1, and we'll see how you guys do. Okay, so first of all, we have to relate cubed root of 1.1 back to g of x to determine the x. And then once we determine the x, we can use our linear approximation to finish out the problem. Okay, so if we're looking at the cubed root of 1.1, and we know that g of x is the cubed root of 1 plus x, that means that x has to be 0.1. Okay, so here's our thought process. We want to approximate the cubed root of 1.1. Turns out that's g of 0.1. 0.1 again is fairly close to 0. It's fairly close to 0. So we can say this is going to be approximately 1/3 times 0.1 plus 1. Okay, and then, we can put that in our calculator. We can even do that by hand if we wanted to, just some basic arithmetic. And now we have a nice approximation for the cubed root of 1.1. Again, cubed root of 1.1 is hard to calculate by hand, but this linear approximation is easy to calculate by hand. All right, so there you go. Okay, so let's look at another example of how we can use this. What's up next is we're going to approximate 1 over 4.002 using linear approximation. Okay, so notice in this one, they don't give you a formula. They don't give you a curve. They don't give you an A. So when we're talking about linear approximation, we know we need those things, right? And again, a good first step is always to pick up on that key word. And we know with linear approximation, we need a function and we need an A. And we could see that because linear approximation uses the tangent line. Okay, so Again, that's why it's good to pick up on those keywords and write out the formulas. So that's going to kind of lay out our strategy. To use linear approximation, we're going to need an f and an a. We're going to need a function and a value. Okay, if we'll look at 1 divided by 4.002. And we have to think what would be the easiest route, right? Not making our function overly complicated, not making our a something crazy. But what would an easy function be to relate back to 1 over 4.002? And what would a good a be? Well, I would choose, I see the big number is down here in the denominator. So I might choose something like this. F of x equals 1 over x. And then what's a number that 4.002 is close to? 4.002 looks like it's close to 4. So let's make a linear approximation for f of x equals 1 over x at a equals 4. And then we can use it to approximate this. All right, so just to kind of relate it back to this example up here, they just jumped in and they wanted you to approximate these values without giving you g and a. So we had to be a little bit creative in our example. We had to figure out the function and the a value first, and then we can use it to approximate values close to a. So that's what we did. We kind of stared at it and said, okay, 4.002 is close to 4. So let's make it 1 over x, where a is equal to 4. Okay, so let's see. We have f of a. That's what we need. F of a is going to be 1/4. And then we need f prime of a. Let's see, f prime of x. Let's think of 1 over x as x to the negative 1. So we don't have to use the quotient rule, right? So then we're looking at negative 1, x to the negative 2. Okay. So then if we plug in 4, we're looking at negative 1 over 16. Okay, so let's start plugging in our linear approximation. And again, that linear approximation is just the tangent line at 4. So L of x is equal to f of a plus the slope, plus a negative is just going to make it negative times x minus 4. Okay, and there you go. And now we're going to use this line to approximate this. All right, because notice 4.002 is very close to 4. So here's our train of thought. So 4.002 is equal to the function we created at 4.002, which is approximated by our tangent line at 4.002, okay, which is this right here. Okay, so it's 1/4 minus 1 over 16 What is that? I don't know what that is, so I'm just going to make it go away. Okay. And then notice this has really just become the difference between 4 and 4.02. Okay, something like that. And again, we can calculate this fairly well. This is just kind of like an arithmetic problem. And we get our final solution. So 4.002 is going to be approximated by 1/4 minus 16th times 0.002, which ends up being 0.249875, something like that. All right, and then there you go. So why don't you guys try to do something similar? I'm going to see if I can. There we go. Trash that. And you guys are going to do the following. You guys are going to approximate the square root of 100.5. Again, this would be difficult to do by hand, but we can easily do it using linear approximation. All right, so go ahead and push pause and then come back and see how you did. Okay, so remember linear approximation, that's your keyword. And so you would say that f of x can be approximated by L of x, the tangent line. This is the equation of the tangent line. It's not a new equation, it's just the equation of a tangent line in terms of derivative. So it means we need an f and we need an a. Okay? And there's a lot of different ways we can do this. I always like to just try to pick a straightforward function. And I think choosing something like the square root of x would work. You can also do something like 100 plus x, the square root of 100 plus x. That would work as well. If you chose 100 plus x, everything will be the same. Just, it just might, I'm sorry, not, your final answer will be the same, but just the works in between will just look a little bit different. Okay, and then if we let f of x equal root x, then what would your a be in this case? What's 100.5 close to? It's close to 100. Okay, so let's see everything we need in here. We need f of a, square root of 100 is 10. We need the derivative, okay, so the derivative of the square root of x, that's like x to the 1/2. And we're going to figure out these values at 100. So again, f of 100 is the square root of 100. So it's 10. And f prime of 100 is 1 over 2 times square root of 100. So 1 over 2 times 10, or 1/20. Okay, so then the linear approximation, again, which is just the tangent line at the point 100, is going to be approximately f of a plus the slope of the tangent line times x minus a, and we're saying a is, again, 100. Okay, so there you go. And then why do we do this? We're going to use this line now to approximate 100.5. Okay, so square root of 100.5, how does it relate back to our f function? It would be x is 100.5. So it would be this, right? Okay, and now this is approximated by our tangent line at a equals 100. Okay, something like that. All right, and now this problem right here is an arithmetic problem, whereas figuring out the square root of 100.5, that's much more difficult. All right, so there you go. We calculate that last part. So the square root of 100.5 is approximately 10.025.